the road that takes us on. Types of HVAC systems that are available, and there's a reason why I have some of these in parentheses, but DX, a direct refrigerant, much like your refrigerant in your condensing unit at home, it's just direct. There's refrigerant right inside those pipes. Chilled water systems, in fact, they are direct systems inside the chiller, and they're indirect outside. We just use a heat exchanger to run chilled water across those cold surfaces and generate chilled water. But so they're, in terms of the refrigeration, they're direct. Hot water systems, boilers and so forth, and I have in parentheses hot. There's a reason why. Steam, again, hot, 212 degrees or better. Electric heat, again, hot, probably in the 200 to 300 degree range. Geothermal is mild, probably 120 to 125 degrees is the standard condition in terms of what we want to generate out of geothermal on the heating side. So we're going to go back to school here a little bit. Thermodynamics, explaining what's going on within these systems. When you expand a gas, it gets cold. It's pretty simple, okay? The air that's in the tire in your car is a refrigerant. Notice anytime you put your finger on the needle and let air out of a tire, the tip of your finger gets cold. There's a reason for that. That air is rapidly expanding from the inside the tire to the outside, and you have a refrigeration effect that's going on. Okay, now, fact is air is a very poor refrigerant. It would cost us huge amounts of money to try to cool our buildings with air, but it is in fact a refrigerant because of this thermodynamic principle. And the opposite of that is when you compress a gas, it gets hot. Okay, so when you have an air compressor at your house and you're compressing it, if you actually feel the tank, that tank gets a little bit warm while you're compressing gas. Those are the two key principles that are pretty much in operation throughout our refrigeration, air conditioning systems and our refrigerators. It's that simple. So here's understanding a refrigerator. Okay, you have a compressor, and the compressor is compressing the gas, and when you compress a gas, it gets hot. So the flow's going in this direction, and now you're in a heat exchanger, and inside these coils you have a hot gas, and you have geothermal water coming in at 65 degrees, for instance. It's washing across that hot coil, and as it washes across that hot coil, it may go out at 75 degrees. As it picks up the heat and washes out into the geothermal field, what's happening is this refrigerant inside here is getting cooler. Okay, you're taking the heat out of it. As it goes now into the next phase, it goes across an expansion valve. You've already taken a lot of the heat out of this refrigerant by washing the water across from the geothermal field. At this point, when you expand a gas, it gets cold. So now inside these pipes, you have cold refrigerant, and this is your evaporator inside your furnace, or this is that coil inside your refrigerator. But basically in between your freezer and your refrigerator, this is a cold surface. It's making the inside of your refrigerator cold. It's picking up the heat inside your refrigerator, ultimately warming the gas, and we start the process all over. So I'm asked about geothermal systems, not so much as of late, but for the last 15 years or so, people would ask, well, do you really think this technology is around? Is it here to stay? And I sort of chuckle when I ask them how do they feel about their refrigerator. You know, it's been around 70 years. Everybody's comfortable with it. Nobody worries about it. The fact is we've come to know and love them, and we don't even think about it. It is the exact same technology that we're using. A refrigerator, in fact, is a heating device. Look on the back of it. There's that black coil. That's just getting rid of the heat from the inside of the box, and we're just using this process. So, in fact, a geothermal system is nothing more than that. We're just using the earth temperature to cool down or heat up that coil depending on what process we're in. So actually it's fairly simple. So if you're comfortable with your refrigerator, you should be comfortable with geothermal. It is the same technology. This slide, spent a lot of time with it, reversed it and flipped it, and we call it now a heat pump. So in essence, what's going on here now is we still have the geothermal water, the compressor's here, and this is a heating. On this side, we're compressing the gas, and we're blowing air, for instance, inside your house. We're blowing the fan across this hot coil, and we're heating the house. It's cooling down. It's then expanding through this expansion valve. It gets cold inside this coil, and guess what? We're washing water across that coil and out. So we may be coming in at 45 degrees. This coil is cold because we're expanding the gas. we're taking that heat off, taking that coldness off of it and washing it back out at 38 degrees, and the process continues. So when you flip, on your thermostat, when you flip that little switch from heating to cooling, there's a reversing valve in there that's just basically switching the valves across, and you're reversing the refrigerant flow within the heat exchanger. And that's all that's occurring. But it's the exact same process. We're expanding a gas, we're compressing a gas, and we're using those two principles to either wash heat off the heat exchanger or add heat to the heat exchanger. So typically in a air-to-air heat pump, this is a heat pump here, and air-to-air, the same process is occurring. This coil either gets hot or cold, and it goes to the ductwork, and it heats and cools your house. These systems in the 80s really got a bad name for themselves, and because they weren't highly efficient, they would blow maybe 85-degree air. Well, you can heat your house with 85-degree air or 80-degree air, but most people felt drafty, and they got a bad name because they didn't have enough lift. They didn't have enough efficiency to them. Even today, that's changing quite a bit. In a geothermal system, we basically take that same home, and now we put the compressor inside the house unit, and we put a pump on it, and we just wash the water through a geothermal well field. Okay, so this condensing unit, this unit here, if I would simply unravel the outside of it and lay the coils out and bury them into the ground, and I could get enough heat exchange surface off of them, I would have a geothermal system at that point. All I'm trying to do is get rid of the heat and get rid of the cold. In most of the environments, we just put a big fan across it, taking energy, and force the air across it so we can force the heating and cooling effect. In geothermal, we don't have that fan to force it. We need a lot of ground and surface area in order just to get rid of the heat. So typically, these holes are 300 feet deep. Residentially, they may be 150, typically 300. And depending on the tonnage and the load of the house, we would size the field. There's also horizontal loops. If you have a lot of ground area, you can do this. Slinky loops and ponds. Again, you have to size this depending on the load of the house. So if you have a big home or you have a big commercial building, these loops get very large. You have to have a huge lake, or you have to just put a lot of holes in the ground to have a heat exchange surface. Back to class again. Entropy. Entropy is the order or the disorder of the universe. Okay, and to me this is a key principle here. It's a fairly deep principle, but the fact is that all the systems that we utilize are high entropy systems. We use coal, we use oil, we use all those high energy systems that are compact. You can hold them in your hand and know that you've got a gallon of gas and you can do a lot of damage with a gallon of gas. You can go a fairly far distance with a gallon of gas. It's a compact energy source, okay? The fact is that we're burning that up. That's the carbon sources. And these low entropy systems, these systems that have a disorder to them, are everywhere. The fact is we do not have an energy crisis in the United States or in the world. What we have is an economic crisis for our energy. There's energy everywhere. Okay? It's in Pennsylvania, it's in Utah, it's in North Dakota, it's in the wind, but we can't afford to extract it. Okay, it's because those systems are low energy systems. They're low entropy systems. The energy is spread and disordered, and it takes a lot of energy to reorder them so that we can use them. And because it's cost us a lot of energy to reorder those systems, we have just chosen as a culture to burn coal and burn oil. It's easy, okay? So entropy is basically, again, it's the order or disorder of the universe, and energy is a lot like that. So if you look at this photograph here, the question is that if you let your teenager not take care of his room, does it get cleaner over time? The answer clearly is no, okay? If you let your house go and don't paint it, don't take care of it, don't do any maintenance on it, does it get better over time? The answer is no. Entropy, which is a law in physics, states that everything basically flows downhill. Everything is going to go to disorder over time. And so we have to put energy into it in order to reorder the system. So thankfully we have the sun that's constantly putting energy back into our system and allowing us to reorder our universe to some extent. But if you drew a box around the sun and the earth, ultimately those two systems are becoming more disordered over time. In fact, they say, what, in billions of years, the sun's going to fail us. Okay, so I want you to understand that we have to always put energy into systems to reorder them. So when getting back to where I had things in parentheses, boiler systems 180 degrees, fairly high ordered systems. Geothermal systems, less than 120 degrees, low ordered systems. Photovoltaics, 12 volts. Power transmission, 265,000 volts. Hoover Dam, 20,000 gallons per second at peak. Notice that the technologies that we're heading into are going to be utilizing disordered systems. COPs, coefficients of performance, and SEERs, seasonal energy efficiency ratios. My comment with regard to entropy and so forth is ultimately I use this as an example. You go to a wedding and they've got the blue sand and they've got the red sand up at the, and ultimately the couple pours the two sand together and they go, well, the two shall never be separated again. You go, my goodness, that would take a lot of time to separate all that. So that basically that becomes a very high disordered system. When you had the red sand and the blue sand, they were fairly ordered, okay? When you mix them, it becomes disordered. Well, the fact is that energy is a lot like that, and that ceremony would have a completely different meaning if, in fact, you could throw a penny's worth of energy in it and watch the sand separate. Okay, just like that. I'm out of this. I could separate the sand. Okay, that is what a heat pump is doing. So a heat pump is basically able through that refrigeration cycle to take energy at low levels. 50 degrees inside the earth, 60 degrees, whatever the number is, and reorder it. Pump it up through a refrigeration cycle and get it to maybe 120 degrees, which we can now use. So we look at COPs. When I started in the business 30, 35 years ago, COPs were typically around 2. I can remember hearing numbers of 1.5. What that says is that for every $1 that you give me, I will give you back $1.50. And you go, not a bad deal. So we were using air-to-air heat pumps and at least going towards heat pumps in some of our technology. The fact is, though, that wasn't enough savings in order to compensate for the high expense of a well field and a geothermal system. So in the mid-'80s, we were probably in the 1.5. In the early 90s, we were probably in the 2, 2.5. In the late 90s, we were probably in the 3s, 3.5. In the 2000s, right around 2000, we were probably 4, 4.5. Right now, we're sitting at about 5.5 to 6 COP, and within the end of the year, there are manufacturers saying they're going to get to 7. So now, you give me $1, I'm going to give you 7 back. All of a sudden, the economics have turned. It's now completely available to have an economical analysis on geothermal systems and make it relevant. Okay?